Whoop, whoop. What up, athletes? Let's do this today. Oh, excuse me. All right, here's your warm-up. I better move my picture out of the way, though, or that's not going to help you. According to Lifehacker, the graph illustrates the best time to arrive for a job interview. Use the graph to answer the questions below. Let me just move this a little bit so you can see all the questions. Go ahead, pause me, take a second, and answer these questions while I pour coffee. Even after that, I'll start, but you can always pause and take longer. I love coffee. It's true. Awesome. Let's look at this. We see a graph everywhere from good luck to perfect. And these are minutes past the scheduled start. In other words, if it's negative, you're showing up early. If it's positive, you're showing up late, anything past 0. So here's what we're finding out. According to the graph, what is the range of time that a person should arrive? If you want that perfect money time right here, it looks like that range is, golly, if I'm looking straight down, that looks from about, I don't know, 17 minutes ahead of time. See if that's 15. It's about a third of that. I don't know, anything from, I would say, about 16, 17 minutes ahead of time. So, from negative 17, clear up until, what does that look like? 12 minutes ahead of time. So X is somewhere in between 12 and 17 is what I think. You could go easy and say, hey, well, I mean, that's about what if your numbers are a little different, that's fine. But that's just saying you're showing up anywhere from 12 to 17 minutes early. That's what it looks like to me. What happens to a person's chances of getting the job when they arrive too early? Well, depends. If you're way, way too early, they go down. Not to 0, but they just go down. You don't want to be, like if you're an hour early, it doesn't look like it's looking good. But anywhere from 45 minutes early to about that 17-minute mark, early mark, we see your chances going up. So what happens to a person's chance of getting the job when they arrive too early? Well, it's better than when they're too late, right? It's better than when they're too late. So they go up from negative 45 to negative 17 approximately. Remember, I'm estimating based upon what I can see from this graph. These are 15-minute increments, right? So it's like we've got to guess it out a little bit. What happens to a person's chance of getting the job when they arrive too late? Well, we see that quickly goes to 0. Goes to 0 after about 2 minutes. So in other words, if you're about, let's see, after 2 minutes, that looks like about 2 minutes right there. And it's pretty close to 0 anyway. How late could a person arrive and still have a chance of getting the job? I would say it's right about 2 minutes. I think that 2 minutes is what it's telling me right here. Describe the difference between arriving early and arriving late. I'm not going to write this all down, but I will explain it to you. No matter how early you arrive, you have a better chance, no matter how early you arrive, of getting that job than you do the very second from on time to late, right? So once you're late, you pretty much have close to a 0 chance of getting the job. If you're early, if you're too early, you still have a chance of getting the job. If you're in that perfect early pocket, you have a great chance of getting the job. And then it just drops off significantly from there. It's pretty amazing that even though this person is early, you notice they very quickly are losing, because employers are looking for somebody that doesn't just show up on time, but that shows up ahead of time to be able to be prepared for their job as soon as that job starts. So, hey, Good application of that math right there. All right, let's move on. Today's going to be pretty quick. We're talking about sketching graphs of functions. And again, I find myself in the way. You can sketch the graph of a function using its key features, knowing the domain, range, intercepts, behavior, and extrema of a function, as well as intervals where the function is increasing, decreasing, positive, or negative, provides a clear idea of what the graph of the function looks like. Drag the labels to the graph to identify its key features. Well, let's see. This in behavior is, let's see. This in behavior is increasing, right? So remember, we read a graph from left to right. So this is going up, which is why it's increasing right here. Let's follow this up. We get to a maximum point. It's increasing on the left, decreasing on the right. That's the local maximum or relative maximum. Now we're going to go down. Oh, this is this point right here. What are we doing? We're decreasing. We go down, 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 and now we hit another stopping point where we're going to switch. Sorry about that blip. Had to get a tissue. But anyway, we're switching paths here. We're going to start going up again, which means this is a relative minimum. No, it's not the lowest. It's lower over here. But it is the point where the graph is changing, so we call it a relative minimum. And then we see what we're starting to do. We're going up, up, up to the end, so we're increasing on this end. So on the left side, our in behavior is increasing and increasing on both ends. Okay, so this is what's happening with this graph. All right, now we're going to model some situations, see if we can pick the graph that best fits. So in 2015, Christopher Stresser set a new 24-hour cycling record by riding 556 miles in a 24-hour period. I don't even like to drive that much in a 24-hour period. The distance he rode over the 24 hours can be represented by a function. Move through the slides to see how to use the key features to sketch a graph that shows the distance traveled y as a function of time x. Distance traveled y. So we see our distance traveled in miles y right here and our time on the x. And every tick mark is growing by 2, 4, 6, 8 in hours. Every tick mark on the up is growing by 50, which makes sense. We need to get to 600. And let's talk about what this graph is doing. So we see no distance has been traveled at the y-intercept and no distance or time, right? So that stands for 0 hours, 0 miles. This is linear and nonlinear. The graph of the function is linear. We're going to assume a constant speed throughout. Positive for time greater than 0. So as time goes up, he's moving forward, and increasing for time greater than 0. In behavior, as the number of hours he has ridden increases, the number of miles he has traveled increases. So again, it's linear. It's just going up, 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 up. So now let's actually go through this. Before sketching, consider any possible constraints of the situation. It is not possible for Christopher Stresser to ride for a negative amount of time. So in other words, we're not going to have a line that extends past here because we can't have negative time. So the line has to start at 0, 0. Does that make sense? We can't go negative time or negative distance. So we're starting here. It's really just a ray. It's going to be going up this way. Therefore, the domain and range are restricted to non-negative x and y values, and the graph only exists in the first quadrant. Okay, 0, 0 represents, we got our point right there. 0 hours ridden, 0 miles traveled. The graph is a straight line that is positive and increasing for all hours ridden. So it's up to 24 hours, and at 24 hours we know it's what, 556 miles, right? So we're putting 556 right there, connecting those 2 points. And then what do we know? As x increases, y increases. So that means we're going to keep this graph going because we're going to assume that if he kept going, maybe he's going to keep cycling the next day. It's just going to keep going further and further up. When he has spent no time riding, no distance has been traveled. The more he spends riding, the more distance will be traveled. That's what we can say about this graph. All right. So let's go on to the next, where we're actually going to match some graphs up to a situation for the next two. Maggie is taking a road trip and decides to keep track of how much gasoline she is using. She notices that the amount of gasoline used by her car depends on the distance she has traveled. So let's talk about this now. Which graphs could be used to show the amount of gasoline used as a function of distance traveled? Okay, so in other words, we have gasoline on the y, distance traveled here. The more distance she travels, the more gasoline she's going to use. So the y-intercept, no gasoline has been used when Maggie has traveled 0 hours. In other words, we're out here at 0, 0, no gasoline has been used. Now here's the thing, we can right away from that eliminate some of these graphs. Because look, these all start, that starts at 0, that starts at 0, that starts at 0, great. This one starts at 0 right here, great. But notice these two. E is starting at 2 gallons used, and D is starting at 8 gallons used. Well, this says the y-intercept is no gasoline has been used. So right away, D and E are dead to us. They're gone. We know they're not the thing. Linear or nonlinear? The graph of the function is linear. Well, the remainders are all lines, okay. Positive for distances greater than 0 miles. Well, again, we could have canceled that one out because it's negative. And we're going to be going in positive for distances greater than 0 miles. That's positive, that's positive. This is positive, and this is positive, okay. In behavior, as the distance increases, the amount of gasoline used increases, okay? So it's going to end with it increasing and increasing, not stopping. So what do we see right here? B is gone because B starts at 0, 0, which is great, but notice it ends here at 250. Well, we're not told this ends at 250. We're just told that the end behavior is increasing as the distance increases, the amount of gas increases. The way it does that is we show that with an arrow on the end. So now we're locked into A, B, or F. And we can eliminate F because we can't have negative gas usage, can we? Or negative distance traveled. So F is gone because it starts at 0, 0. So we're down to A and C. And since we're not told the speed, both of those are possibilities. Okay, A and C are both possible. All right, let's go to our next one. Why don't you pause it, take a minute, I'll read it, and then after that, pause it and take a minute and see if you can match it to the right graph. It says, use the key features to identify the graph. Positive for all values of x, increasing for x is greater than 1, decreasing for x is less than 1, relative minimum at 1, 4. In behavior, as x increases and decreases, the value of y increases. So no matter if x is going less or going right, the value of y is increasing. Okay. A lot to unpack here, so go ahead and take a minute, pause it, we'll get back to it. All right. A couple of things. One, let's look for that 1, 4. It says that's a relative minimum. Well, I can go 1, 1, 2, 3, 4. We have that point, but on this graph, that's a relative maximum, so A is gone. 1, 1, 2, 3, 4 isn't even on C, so C is done to us. Now we're looking at B and D. We have 1, 1, 2, 3, 4. That is a minimum. 1, 1, 2, 3, 4. That is also a relative minimum, so it could be B or D so far. We're left on that. All right. Increasing for x is greater than 1. We see it increasing. X is greater than 1. Increasing for x is greater than 1. Those are both still good. Decreasing for x is less than 1. That means if I read it left to right, for x is less than 1, right? So x is over here. If I'm going left to right, this is going down, 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 boom. That's what makes it a relative minimum. This is going down, 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 down. Boom, it stops and is about to turn. That is also decreasing for x is less than 1. And then last, it's positive for all values of x. Well, all values of x, this is going to be a positive graph. Then let's look at the end behavior. As x increases and decreases, the value of y increases. Well, we see as x increases and as x decreases, the value of y is going up and up on both sides. Even though, guys, I know some of you may be going, but Mr. Tim, you said this is decreasing as we go to here. Well, it is when we read it left to right as far as that goes, because we always read a graph from left to right. However, even though the graph is decreasing, the value of y as I go left is still going up. So that's the difference there. And symmetry, the right half of the graph is the mirror image of the left half in approximately x equals 1. Well, if I were to draw that line of symmetry right here, we see this would fold over on that side, and the same for this. So it turns out B and D all the way through are correct answers. Let's check. Boom, look at that. All right, that's it for today. You're going to sketch some graphs, going to match some graphs and do some problems. It's going to be amazing. With that said, peace out.